Now that we've talked about all the things that are needed to construct an actual interval, let's actually go through the process of constructing a confidence interval. And a confidence interval is built by taking some estimate or statistic and adding and subtracting a margin of error to get a lower bound and upper bound. And remember, we talked about the margin of error being, we know the standard deviation. Secondly, we talked about it being z star times sigma x over the square root of n. Well, because we're taking these things from samples and we don't actually know the standard deviation, remember we had to go back to the t distribution. And the t distribution is going to give us a different critical value, which we call t star, but it's found the exact same way as c star, and a different standard deviation, which is the sample standard deviation, which we call it S of x. But our margin of error now is going to be this right here. T star degrees of freedom times S of x over the square root of n. And we're going to construct the interval like this, was based all off the normal curve. And so remember the normal curve, let's draw this out. In the normal curve, we want our data to sit, for instance, 95% to sit inside of here. Well, the value that's going to mark the middle of this curve is going to be x bar, or the mean. And then we're going to give it this margin of error to the right, which we call E, and the margin of error to the left, which we call negative E. So this is positive E, negative E. So in order to create an interval, here's how we're creating it. It's x bar, which is the statistic used to estimate it, plus or minus the margin of error. And our margin of error is equal to this stuff right here. So here's where we get our interval from. And we're going to be able to calculate this by hand now. So let's go ahead and actually do an example with this. So here's our example. It says you randomly select 36 cars of the same model that were sold at a car dealership and determine that the number of days each car sold on the dealership's lot before it was sold. The sample mean is 9.75 days with a sample standard deviation of 2.39 days. Construct a 99% confidence interval for the population mean number of days the car model sits on the dealership lot. So we're going to construct this 99% confidence interval, right? In order to construct it, here's what we need to know. We need to verify a couple of things. The first thing, the most important thing you always should verify is that the distribution is some kind of way normal, because you need to have that normal curve available to you. And it doesn't say that it's normal, but we can verify that it's normal by this right here, these 36 cars, which is your n. And your n is 36, which that number is greater than 30. So by CLT, the mean is going to be approximately normal. But the mean of the population, or in this case 9.75 with the sample and standard deviation of 2.39 divided by the square root of 36. So here's what we need. We have n equals 36. And the other things that we need to create the interval, here's what we need to create the interval. We need x bar plus or minus the margin of error. So it'll be t star with its degrees of freedom times S of x over the square root of n. So we need an x bar first. So let's go and see if we have an x bar here. And we see that the sample mean is 9.75. So my x bar is equal to 9.75. We also need a margin of error. In order to get the margin of error, we have to have two things, or three things. We need a t star, we need a S of x, and we need a square root of n. Well, from the problem, we can see that S of x, the sample standard deviation, is 2.39. Now we can also see that, well, they give us that the n, we found that earlier, was 36. The only other thing we need is t star. Well, we're calculating t star based off degrees of freedom and off the confidence level. And our confidence level is 99%, right? So to calculate that, calculate the 99% confidence for t star. Remember, we draw the curve. And on the inside of the curve, we want to have 99%, which means that there's 1% on the outside, which means that this side is 0.05%, right? So we're going to calculate in our calculator inverse t, 0.995. And our degrees of freedom, well, if our n is 36, our degrees of freedom are 35. And so when I calculate that value, I get a t star with degrees of freedom with 35 degrees of freedom equal to 2.724. So now all we have to do is plug these numbers in to the formula. And the formula reads like this: x bar, which is 9.75 plus or minus s of x, t star, which is 2.724 times s of x, which is 2.39, divided by the square root of n, which is 36. So this is the formula. Here's how you're going to calculate this. When we calculate it, we're going to calculate this margin of error first. And so that value there, 2.724 times 2.39 divided by the square root of 36, which is just 6. This entire value right here is 1.08506. And we're going to do 9.75 plus or minus that. So we're going to do 9.75 minus that first. Doing minus is going to give me the lower limit. So when I do minus that, I get this, 8.66494, so I'll say 8.665. Here's your lower limit. Your upper limit, you're going to do 9.75 plus 1.08506, and I get 10.835, which is the upper limit of this. And so what this is saying is that if we didn't know anything without any information other than the sample is giving to us, we expect the true mean value of the number of days that for the car to sit in that lot to fall somewhere in between these two values. And if we constructed these intervals using this method a bunch of times, sampling this way a bunch of times, then the true mean value would fall inside of here 99% of the time, which means only one of our intervals will miss this value. So now let's look at one more example. In this example, notice off to the right, we have actual values that are given to us, data is given to us. This was done in Excel, and these are summary statistics that are provided for us. So we're going to calculate an interval for this, and it says, psychology experiments sometimes involve testing the ability of rats to navigate mazes. The mazes are classified according to difficulty as measured by the mean length of time it takes rats to find the food at the end. One researcher needs a maze that will take rats an average of about 1 minute to solve. He tests one maze on several rats, collecting the data shown. The summary statistics for the data have been calculated in Excel and are shown to the right. Construct a 90% confidence interval for the true mean time of the maze. Would you support the researcher's claim that the mean maze time length is 1 minute? Explain your reasoning. So here's what we're going to do. In order to actually calculate the interval, remember we need these things. Is x bar plus or minus some t star with its degrees of freedom times s of x over the square root of n. So let's go identify those things in this table. First thing we need is an x bar. Well, x bar is the mean, and the mean is sitting right here at the beginning. So your mean is about 52.20. We'll say 52.21. So we'll call x bar 52.21. Next thing we need is t, and we're going to have to get that from the calculator. So we'll skip over that, and we'll go to s of x. S of x is equal to the standard deviation. Our standard deviation is sitting here. And so that means that S of x is 13.56, we'll say 5, rounding 3 decimals. The next thing we need is n. Well, our n in this particular case is going to be this thing that's called count down here. And they tested it on 21, so our n is 21. And if n is equal to 21, that's going to lead me to my degrees of freedom to find t. And if n is 21, then the degrees of freedom are 20. So this is everything I need to actually calculate it. And here's what I'm going to do. I'm going to write this out, and I need to go find t star first. So t star at 20 degrees. So in a calculator, that's going to be equal to 90%, so that's 90.95 second bars. Inverse T of 0.95. And our degrees of freedom are 20. And I get a T star of 1.7247. Now, using all this information, as we're going to do, we're going to go ahead and write it out. So set it up. It'll be this. It'll be 52.21 plus or minus 1.7247 times S of X, which is 13.565 divided by the square root of 21. And so let's go ahead and calculate these values. So again, we do this margin of error part first. So 1.7247 times 13.565 divided by the square root of 21 gives me, this number is 5.1053. So we'll stop there. And so we're going to add 52.21 to that. 52.21. We'll do minus first. Minus 5.1053 gives me a lower bound of 47.105 and an upper bound of 52.21 plus 1 plus 5.1053 gives me upper bound of 57.315. Now, here's the actual interval from our confidence interval we have gathered from our data at 90%. Question is asking, would you support the researcher's claim? Would you support the researcher's claim that the mean maze time length is 1 minute? Yes or no? Well, based off this interval, let's look at it. The interval goes from 47 seconds to about 57 seconds. So do you support the researchers claim the mean maze time is about 1 minute or is 1 minute? No. Why not? Well, if it were 1 minute, what value should sit inside of this interval right here? We should see 60 seconds sitting inside of here. And because we don't see 60 seconds inside of here, what does that tell us? Well, if you look at the values, 47 and 57 are both lower than 60 seconds. So what does it say about the difficulty of the maze? It's probably too easy, or it's not the minute that the researcher is looking for. And again, we can tell that because if it were the value, if it were 60 seconds, a plausible value of 60 seconds should sit inside of here. Remember, a confidence interval describes the plausible values. And these plausible values range from 47 to 57 based off of this data. So can we say it's 60 seconds? No. And that's all because that value does not sit inside the interval.